In this last learning sequence of block 1, we will talk about probably most important distribution, or at least definitely most known distribution in statistics, which is called normal distribution. This learning sequence will be quite long because we are going to talk about all details, what normal distribution is, also how to estimate parameters of this distribution, and many different examples, exercises, and so on. But let's start with talking about why actually uniform distribution that we learned in the previous learning sequence is not well suited for describing the real experimental data. Let's recall that in uniform distribution, we assume that any event have equal chance to occur. But when I say not very well suited, it's not fully correct because, for example, when you roll a die, it follows kind of uniform distribution. But what about the experimental data? Let me show you an example where I try to use uniform distribution, theoretical uniform distribution, to describe height of people. So in this case, you can see that I have PDF, CDF, and ICDF function. So I'll remind you, PDF function, it's a probability density function. It shows you density of different parts of your values, range. CDF gives you a probability if you know a value. And ICDF, inverse CDF, gives you a value if you know a probability, right? So in this case, you can see a uniform distribution describing population of adult people whose height is distributed between 140 centimeters, that's the minimum, the smallest value, and 220 centimeters, which is the max. So these are two parameters of a uniform distribution. Let's try to use this theoretical distribution to do some calculations. For example, let's find a chance that if we select a random person and measure height of this person in this population, this height will be below 150 centimeters, right? So we know how to do it, right? So first of all, the easiest way to do it is to use CDF function, cumulative distribution function, where we simply provide the value. We know the value, 150. And CDF exactly gives you a chance to get a value below 150, right? So it means that if you do this experiment again, the chance that height of this new person randomly selected from this population will be below 150, that's exactly what CDF gives you. So in this case, it's 0.125. You can think of this value as 12.5% of people in this population have height below 150, right? And then you can also do it, for example, by calculating area under the PDF curve, which will be apparently also 0.125. And then, of course, for example, if you select 125 here, you will get 150 here, right? So this is what we learned from the previous learning sequence. Now let's try to find another probability to get a person whose height is between 165 and 175 centimeters. And if we do this again, so in this case, we have two values. So first we find a probability to get a value below 165, then to get a person whose height is below 175 centimeters, and then we take a difference of these two probabilities. And if you take a difference of these two probabilities that is equal to area between these two values, so again, here we have 165 and here we have 175 centimeters, you will get 0.125 again. So it means that, again, 12.5% of people have height between 165 and 175. And if you think about what you observe around you in this world, you kind of don't believe it because we know that most of the people actually have height between approximately 165 and 175 centimeters. This is what I would say the most expected range of the values, right? While very few adult people have height below 150 centimeters. And then the result that probabilities are equal kind of does not correspond with our experience from the world, our observations, right? Now, what I'm going to do, I will get this table that I used before in the first learning sequence about distribution of height of adult people in the United States. So you can see that in this case, we have percentiles, we have male height and female height. What I'm going to do, I will simply take female height and I will transform the inches to centimeters, so it's a little bit easier. And this is the percentile. So you can see, for example, approximately 1% of all females in the United States have height below 144 centimeters, 10% have height below 153 centimeters, 25% have height below 157 centimeters, and so on and so forth. So this is the table. based on empirical results. So this is the table of observations in United States, right? Now what I'm going to do, I will make the percentile plot. You remember in percentile plot, we have values here, and then we have these percentages here, right? And then we remember from the previous learning sequence that actually I'll also show you here. So this is how the plot should look like, right? Because CDF function, it's a theoretical function for the percentile plot, for the percentage plot. So it should be a straight line, but you can see that apparently we don't have a straight line. So our points, they have a kind of S shape here, right? So it's not a straight line. So definitely what we see from this table doesn't match very well to our expectations if it's a uniform distribution. So apparently it's not uniform distribution, right? Now what I'm going to do next, I will make a distribution histogram. So I will compute beans. I will simply take these differences. So my beans will not be equal, right? So these are my beans. For example, I take all values below 144 and I know it's 1%, right? And then how many values I have between 144 and 153 centimeters. I know that 10% have height below 153 centimeters, 1% have height below 144 centimeters. So how many I have in between? Exactly 10 minus 1, so it's 9%, right? And then I can do the same. So this one, it's this minus this, so it's 15%, and so on and so forth. So now I have relative frequencies and the beans, So this is my frequency distribution table, and I can use this frequency distribution table to make a histogram. So this is the histogram for relative frequencies. So see here I have relative frequencies. And to remember again that if you think about theoretical distribution, if it's uniform distribution, then PDF function, probability density function, it's our theoretical function for the histogram. And definitely it doesn't look like a rectangular shape, right? So it looks like a, I know, like a bell, right? So you have most of the values are located in the middle, and then you have very few values on the tails. That's what we already called central tendency. So most of the values, they tend to be located in the middle of your distribution. Well, this is relative frequency. What happens if we compute densities? So here I compute densities. How I do that? You remember density, it's when you take relative frequency and divide two widths of this bean. For example, this bean has width of 9, so 0.09 divided to 9 centimeters. So this is the density, right? So it means that 1% of value per centimeter. Here we have 4% of values per centimeter, and so on and so forth. So now I can make a distribution of densities, and we still see a bell shape. It's not perfect bell shape, but apparently we have the central tendency again. So most of the values, they are located in the center. Well, this bell-shaped distribution where most of the values you have in the middle, and then it symmetrically goes down, the density symmetrically falls down when you go from the center to both directions away, and you will observe it very often, especially if your observations or measurements are fully random. They are continuous, so they are measured as continuous values. And they don't have strict bounds. So it means the values is not bounded somehow. For example, imagine that you measure, I don't know, percent of correct answers, then you have these bounds because you cannot have percent of correct answer above 100 and below 0. Then it will not work in this case. But if we don't have strict bounds, strictly speaking, for height we don't have any strict bounds, then this requirement is met. So in this case, in most of the cases, not always, but in most of the cases when you have these three requirements are met, then you will see distribution of these values, of these random values, indeed as a bell shape. So it's bell-shaped distribution. And the idea is that of this bell-shaped distribution is this central tendency. So most of the values you have in the middle, we will call them also most expected values. And then you have least expected values on the tails. Sometimes it will be symmetric, sometimes it will be a little bit skewed, but nevertheless, you have a very clear peak on this distribution shape. If you make, for example, histogram of relative frequency distribution, or if you make a theoretical distribution. Okay. And the practical examples, for example, if you run experiments several times without changing the experimental conditions, you will see that the result of the experiment, the outcome of the experiment, will vary randomly, even though you didn't change anything, right? And then if you make a distribution of this variation, you will see a bell shape. Or, for example, you measure concentration of the same object. For example, you measure concentration of I don't know, pesticides in the same sample of water taken from the lake. So you simply repeat the measurement procedure again and again and again, and your result will slightly vary. And then again, if you make a distribution of these different measurement results, you will see a bell shape. So very often, random values, which are continuous and independent, they distributed as a bell-shaped distribution. So how we can describe this shape? And is there any theoretical distribution which we can use for this description? That's what we are going to talk about in the next video.